This is lecture 34 of Condensed Matter Physics 1. And in the past 2 or 3 lectures, we have been discussing band theory and have developed nearly free electron model and rigorous Bloch's theorem, and have discussed how bands arise in crystalline materials. Today, we are going to focus on specific kind of materials, that is metals, from the point of view of band theory. And along with this, we also discuss a class of materials called semimetals, which by counting of electrons, by counting of states, should not be metals, but they are because of band overlaps. So, we are going to explain that. Now, to start with, in metals, the background periodic potential is weak, and that happens because of screening of this potential by free electrons. So, in a way, it is a self-consistent effect. Electrons get free and then they screen the ions, and the whole thing is consistent with each other. So, whatever we discuss in this, we will assume that there is this free electron model which gets distorted by this background potential. Of course, I will comment on what would happen if the potential was strong. So, in our discussion, free electron model, and that means spherical Fermi surface will be the starting point. So, we will assume that that is a good starting point, and then due to periodic potential, the surface will get modified, and modified a bit, but that is enough to change properties of the system. So, let us start one by one. To develop a visualization, let me start with 1D materials, and then we will generalize it to 2D and 3D and see what changes, if there are any, come because of the dimensionality. So, we established in lectures 32 and 33 that there are these energy bands, and I can restrict the K to within the first Brillouin zone. So, this is the first band, and then there is a gap, and here is the second band. I will just confine myself to these, and then I had made these states n states if there are n cells. Last one is not counted because that is same as the first one. So, there are these n number of states. For n cells, periodic boundary condition. Over n cells, and that means there is one state per unit cell. So, if each cell has one atom, whatever electrons come out of that, they will go into that state. If one electron comes, it goes into that state. Now, the other thing we established was n states implies too many electrons can be filled in one band. So, if there is one electron per cell, this implies band will be half filled. So, let us make that picture. Here is the band, and with one electron it is filled up to this point. And these are empty states out here. What about in 2D and 3D? In 2D, I will just take a simple square Brillouin zone. So, all the Brillouin zones should be filled with electrons if electrons were in the first band. There are n k states in the Brillouin zone, and all these states will be filled if there are 2n electrons, and bands do not overlap. I will explain that little later more. So, there are these 2n states available. However, for one electron system, for one electron per cell, only half of these states are filled. So, what you would have is, here I have the Brillouin zone, and if I were to take free electron model, then only half the area of this Brillouin zone will be filled by this free electron sphere. So, let us see what, just quickly calculate what will be the radius of free electron sphere, the free electron circle in the case of 2D. I would have pi r square is equal to a square by 2, and therefore, r is equal to a by 2 square root of 2 by pi, which is roughly 0.8 a by 2. So, the radius of this sphere, if the electrons were free, would be 0.8 of this distance. This is how it will be filled. So, this is 0.2a out here. You can think of the relative distance and this will be actually closer. So, let me modify it a bit. This will be even closer to the surface if the electrons were all free. This is all filled. Now, as I said, because of the background potential, it cannot be spherical, and we will change that. Similarly, if I have a 3D system, again taking a simple cubical geometry, suppose the Brillouin zone is cubical, that means the starting lattice is simple cubic, and by the way that happens with only one metal, that is polonium. In that case, again I would have a Fermi sphere filling this, and the radius of Fermi sphere will be such that 4 pi r cubed by 3 is equal to a cube by 2 for 1 electron per cell. So, I would have r equals a by 2 times 3 by pi raised to 1/3, and that comes out to be roughly 0.985 a by 2. So, this is much closer to the surface than in 2D. It is very, very close, almost touching. This would be the case in case there are no distortion or no bands. Now, in the simple picture we have done already, in the simple picture in free electron case, and I have 1 electron per cell, and I have therefore band not filled completely. In fact, it is only half filled. In 1D you saw this very clearly. In 2D and 3D I have shown this by making these circles and spheres which are filled within the first Brillouin zone. Keep in mind that all n states would occupy the Brillouin zone completely. So, Brillouin zone is half filled, and if we apply an electric field, then electrons can absorb energy and go to the next state. In free electron case, what we did was we took this Fermi sphere, and if I applied a field in this direction, we shifted it, and these electrons out here and the unbalanced one from here, they contributed to the current. In the band picture, what is going to happen is in 1D, and I will keep coming to 1D because it is easier to understand. Here are these states, and only up to this are filled. If I apply a field in this direction, electron can take energy and go up, and this state is equivalent to this state, and then it will start coming back this way. So, actually the energy is absorbed by electrons and they start moving. So, these are conducting systems. That is the free electron picture. Now, in the case of, actually this I should not make, because this thing just shifts a bit, that is all, because of the collision time. Now, assumption is that E is small enough so that electrons do not get enough energy to jump into the next band. Similarly, in 2D and 3D, the Fermi sphere will shift a bit. That is the free electron picture. Now, what happens when you go beyond the free electron and take into consideration the weak field? So, let us ask that question. What happens if we go to the bands? And what this will do is distort. Well, distort is not the right word, modify the Fermi surface, and you get nice geometrical figures. So, in 1D, I have already made this picture that you have up to this field, and here you can see that roughly the band is like half k square here. So, this remains kind of spherical. In 2D and 3D, it will be more interesting. So, let us take the 2D case. In 2D case, here is the Brillouin zone, and half the area is filled with electrons, and here is the Fermi surface for free electrons. If I make the corresponding, let us say, the band picture in this direction, I would have had the free electron energy given like this, but in reality what is happening is that along this direction the energy goes like this. This is minus pi by a and pi by a. At these points, after a certain k, the energy is lower because of the background potential, and therefore, you can see that along this direction, or this direction, or this direction, or this direction, what you are going to have is lower energy compared to the free electron energy. What would happen therefore is the electrons out here will come to this region and this region. They will go to these regions, so that the energy is lowered, and as a result the highest energy, which epsilon f free was 3 pi square n raised to 2/3 divided by 2 m, that is k f square by 2 m, there is h cross square, would be slightly lower. And what could happen is that given this circle, it will get distorted. More electrons would fill these states, and remember all the Brillouin zone has these states, different k states. So, it will like to fill more states out here and less out here. So, you may have a Fermi surface which looks like this, and these are the states which will be filled. In the extreme case, what could happen is suppose the energy gets quite low because of this background potential, then in this Brillouin zone, what was your initially a surface like this would not even remain closed. It will go here. So that out here these states are filled. It is all symmetric. And you have this open surface. If I make the next Brillouin zone, the surface would look something like this. So, Fermi surface gets distorted. All the states within this filled region will be n number of states. And this would be the Fermi energy. The energy on these surfaces is the Fermi energy. The topmost energy should remain the same all over. So, what has happened is that the electrons from here have gotten transferred here. Electrons from here have gotten transferred here and here. And this is how the surface gets modified. What about in 3D? The same thing would happen. Again, take a simple cubic Brillouin zone for the sake of illustrations. So, I would have had a Fermi sphere which is 0.985. So, it is very close to the surface. In the case of no bands, and this surface would now get distorted, so that the states near the diagonal actually come occupying the states near the surfaces. The diagonal is a little far off from the plane of the Brillouin zone or the Brillouin zone boundary. So, these electrons will start moving towards the sides, and consequently the kind of surface that you would get if I were to take the analogy from 2D is that you will have these states filled on the surfaces, and you may have and on the back side this kind of open surfaces. They are open here, so that this sphere has gotten an open ends on the planes, all the planes, and this spherical thing has come here. In the extreme case, when actually the first band is very, very small, all the states in the Brillouin zone will be filled, but it will be distorted quite a bit, right. So, but that is what it is. You do see this kind of Fermi surface. So, first let us write the result. Because of V r, the spherical Fermi surface of free electrons gets modified and it can join the Brillouin planes, making a circle there, and then they connect with the next Brillouin. This repeats because it's a repetitive system. So, you get this open surface, and an example of this is copper. I showed you for the simple cubic structure, copper has a FCC structure, and therefore, its first Brillouin has that complicated structure, but on the face of it you see that sphere reaching out and connecting the surfaces. So, I will refer you to textbook that you are following, Ashcroft, Mermin and Kittel. Both make this picture of Fermi surface of copper, right. So, now how do you know that this really happens? That is done experimentally. Either you can do the magnetic study using de Haas van Alphen effect, which I am not doing right now, or you can do the something called the angle result photospectroscopy. Both give you this Fermi surface. So, by now hopefully you realize that because the bands are formed, because energy near the Brillouin zone gets lowered, the Fermi surface gets distorted and it does not remain a sphere anymore. And this, if I have 2n electrons in the system, has consequences. So, let us now look at the case of 2n electrons in the system, and this basically means 2 electrons per cell, which is same thing as having divalent material, 1 atom per cell. So, as I said in 1D, and let us visualize it in 1D first. What will happen in 1D? In 1D, thing is very simple. The entire band will get filled. There is nothing else that can be done, and here is the upper band. And you apply an electric field, there is no way for electrons to go. So, these are insulators. Let us look at this system in 2D. In 2D, if I consider this Brillouin zone, again a simple Brillouin zone, this has exactly 2n electrons can be accommodated in the states of first Brillouin zone. So, if everything is very low in energy, all the bands have lower energy, this entire band is filled. And this entire, if I again kind of map it onto the 1D, this entire band is filled. I am showing it just schematically. Now, it may so happen that if I look at the first band, and let me make in the extended zone scheme the second band, and suppose that starts from here. In the first band itself, it will be like this. So, this is the second band. That means, in some direction, it so happened that the potential distorted or modified the energy so much that band energy of the second band was lower. What would happen then? So, if I make this zone again, this was all filled. If the first band was lower, and you can see that the energy would be lowered at these points near the Brillouin zone and where kinetic energy is low. Electrons from this region would come out and start filling this region. So, let me show by blue the electrons that have been taken away. This is the first band from which the electrons are taken away, and they have come to the second Brillouin zone. And this blue indicates first band is not fully filled, and the red indicates that the second band has some electrons in it. Let us see how do I make this picture from free electron point of view. In the free electron case, this is my Brillouin zone. The free electron sphere would be something like this. How do I know that? The area of free electron sphere would be exactly equal to the area of the Brillouin zone. That would guarantee that the number of electrons in both are the same, and this would mean that R is equal to a square by pi square root, which is equal to a by 2 times 2 over square root of pi, which is equal to 1.13 a by 2. So, in this case, this radius out here is 1.12 a by 2. Let me make this picture again. Here is the Brillouin zone, which would have been filled if the band was such that all the energy in that band was smaller. Now, this is the sphere. What will happen is that some of these states now have started getting filled in the upper band. And I will modify this picture once more. This is the just plain distortion. Further lowering of energy would take place if in the upper band you would have lower kinetic energy. So, these are the states that are filled, and the upper band becomes like this. These are the states in the fill in the lower band. So, what is happening is, let me make it a little thicker. Pictorially, what is happening is, here is one band here is the second band, in some direction it has lower energy than this, and I'll tell you how so. You start filling, okay, let me show how the lower energy comes. I'll just erase this and still make the band like this, and I'm looking at one particular plane. This picture, this is the second band, this is the first band, is right at the center. As the kinetic energy starts increasing, I go to higher and higher k, I start filling the first band in this direction. There will come a certain point where the energy here, E, will become higher than the lowest of the second band energy. So, at that point, this fellow becomes like this. As I said, it goes up, and these electrons will start filling the second band, which I will show by blue out here. So, energy starts getting transferred into the second band, and this is what happens. If you go back to this square, I came up to this point, started filling the states, and at a certain point here, the kinetic energy increased so much that the total energy became higher than the lowest of the higher band, and the electrons start getting filled here. And this is the kind of surface that you get. Let us quickly make it mathematical. So, I have this blazon out here. I started filling the states like this, and at a certain radius, the energy would be E at this g by 2, which is this point, plus energy at, let us say this is radius k1, because of that k1, and this should be equal to, and this is the first band. This should become equal to epsilon g by 2 second band plus epsilon second band some k2. So, that now this k2 is the radius for second band. So, once again I had a band, and as I started filling the sideways, its energy kept going up, and at a certain point it became equal to the second band energy. And if I went beyond this, the electrons, rather than filling this, would start filling here. So, this band would be empty out here and filled out here. So, what would happen is that these will be empty states and these will be filled states. So, despite having 2n electrons that will fill the entire first band, implying an insulator, we have slightly empty first band and slightly filled. Slightly filled. second band, and this implies a conducting material. I have explained this in 2D, exactly same thing happens in 3D. And that means if I have a plane and here is g by 2, I start filling the electrons sideways. After a certain radius, the energy becomes equal to the lowest of the second band, and therefore, second band starts getting filled up to a radius k2. Again, the same equation is satisfied, which I can write as lowest energy of first band plus epsilon k1 minus epsilon g by 2, if I were to just talk about kinetic energy, would be equal to lowest energy of the second band plus epsilon k2 minus epsilon g by 2 second, g by 2 first, and that gives how much each band is filled. This will be given as an assignment. And these then become conducting, and examples are Be, Mg, actually alkaline, earth, metals, which all have 2 valence electrons. They have 2 valence electrons. So, there should be 2 n electrons that fill the entire band completely, and they should be insulating, but because of this band overlap, these become conducting, and these are known as semimetals. They do not have as good a conductivity as metals, but they are conducting nonetheless. So, this is the example of that. With this qualitative discussion, let me conclude today's lecture by stating that 1, effect of weak potential on free electron states has been considered. This modifies the free electron Fermi surface slightly because the potential is weak. Then we learned that systems with 1 electron per cell are metallic. The reason being that they can absorb energy, and electrons within the same band can go to higher energy and therefore can move. The Fermi surface in these cases may be a closed sphere, may be a closed one, not sphere, closed one, or have open ends intersecting the Brillouin zone. And third, we learned that divalent atoms, 2 electrons per cell, that means there is one atom there, should be insulators according to what I just wrote in red. But if energetics are favorable, that means bands are overlapping, some of the electrons from first band get transferred to the second band, and the system becomes conducting, because now both bands are partially filled, and the examples are alkaline earth metals. Thank you.